Hello, deep learners. I'm Andrew Ng, founder of DeepLearning.ai, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around the DeepLearning.ai offices and meet some of the teams so that you can see where it all happens.
Oh, hi, Andrew.
Do you want to tell our friends at Pine AI what you do at DeepLearning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on the batch?
How much is going on in this field? There's never a dull moment. You might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so let's you get back to it.
Thanks. See you later.
Let's go meet Kian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey Kian, so do you want to tell the people at Pine AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
Yep, that's really important work. Well, it's nice chatting. And now let's go chat with Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in DeepLearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, Hotel.
Thanks, Andrew.
So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot both from the talks and from each other. And once again, welcome to the DeepLearning.ai community.
Hello and good evening to today's Deep Learning Meetup, where Jörg and Simon are going to show us some use cases around contrastive loss. Halil will describe how to use contrastive loss to cluster time series, which would not be easier to cluster otherwise. And Jörg is going to introduce contrastive loss to make sensor data resilient to sensor noise and use less labels later. They will also introduce the general theory behind that. Have fun.
So Maybe I'll quickly then say something so that while Halil is trying to get his microphone working again, so maybe a 5 minutes. The story was that I think like a month or two ago, Halil and me, we met and both said there's this cool thing, contrastive loss, and we're currently working on it. And Herbert was near here and then also said, okay, do you want to do a talk about it? And we said, yeah, totally. And so we both work with sensor data, which is a little bit uncommon. You will hear more about also the origins of contrastive loss when I'm then talking, and I will say something on that it's originally a lot of image-based stuff, and maybe let's see, and then we will. So this is where the origin started, and we kind of worked then in sensor data. And you will here do things, one on clustering and one on how to kind of mitigate some effects of sensors if you have different data sets, and how to use less labels, which is a classical use case of contrastive loss nowadays. This is got especially popular actually this year, at the beginning of this year. Hinton and also Peter Abil, they both published papers on that. Let's see how Lil is back. If we hear him now.
Hear me?
Yeah, perfect.
Sorry. I mean, I hate technology, breaking last month. We tested this, I think, 10 times, but now, now it doesn't work.
At least.
Okay, yeah, so I heard that you introduced how we actually got to this topic. Yeah, it was actually, yeah, cool, you're also doing it. Yeah. So here we are. And I think we agreed that I was going to go first. So just let me open the slide, and then I'm going to share my screen. And hopefully it's going to work at least until I finish my part.
I hope it also works and for me, but yeah, sure.
So, okay, let me try to show my desktop. Okay, so, yeah, okay, it should be visible right now, I think.
Yes.
Perfect. Okay, so I don't have the Twitch stream open, so please, Jörg, just let me know if somebody has any questions or, or if there is some errors or something. Okay, so my name is Halil Beglerovic, and today I'm going to talk about time series clustering using contrastive learning. So basically, we have this slide which says something about us. So about me, I'm currently working as a research engineer, and I'm a Marie Curie alumni. So I finished a Marie Curie project where I also did my PhD. So my PhD, I was doing it at TU Graz. It was on methodologies for testing and validation of automated wiring functions. I did various stuff and various research regarding scenarios, how to test them, how to validate them, how to classify scenarios. And one of those topics was also unsupervised clustering of scenarios. So therefore, I'm dealing with time series clustering and so on. So I'm going to finish my PhD soon. Next month, I have my defense. So my interests are deep learning, computer vision, programming, open source software, and so on. I have put here in the presentation some links for my GitHub research page and LinkedIn. So later you're going to get this slide, so you can also check me out if you want on those sites. Okay, so I will jump right to it. So agenda, what will I show? So I will show clustering using deep learning. So first I want to bring a little bit this idea of clustering closer to people maybe who do not know anything about it. Then I will talk a little bit about contrastive learning. I'm going to talk about the unsupervised side of the contrastive learning. Jörg is later going to introduce some other terms and show how maybe labels can be used, and also a little bit the history about contrastive learning. What my goal is, I want to give you the intuitive understanding about contrastive learning. Basically, that everybody who is listening right now, it doesn't matter what kind of experience he has with deep learning, that he understands, okay, I understand what contrastive learning does. And at the end, I'm going to show what time series clustering is, and how it can be done, and also how we can apply contrastive learning to it. And I will also show why I think that contrastive learning is actually quite a good match if you want to do some time series clustering. So as I said, I prepared this presentation for all levels, so you do not have to have any knowledge about deep learning. I think I have a lot of graphics, so a lot of figures, and only I think 1 or 2 slides with 2 equations. So I think it's going to be quite easy to follow. Okay, so I will start with clustering using deep learning. So here is an image of like a 2D space where we have some data. And of course, if you're dealing with unsupervised learning, we do not have any labels. So these labels are basically some knowledge, but we do not usually have this knowledge. So this, you can imagine that this is all black, let's say. And what we want to do is like, we want to have an algorithm which is going to produce some clusters like this. And basically what the algorithm needs to do is to group these points together by some kind of similarity. Usually we cannot influence this similarity. So the unsupervised learning or the method is just going to group them by similarity. You cannot influence it that much. And also because it is random, like the models are initialized randomly, you will get, depending on the run, you can get also different kind of clusters. So just intuitively, you can think about this like we have some M&Ms, and let's say we want to sort them by color. And then you have some kind of space where you start from. So you can think about it as a table with a lot of M&Ms on them. And then you have another space, so let's say another table, and you have some freedom on how you put them together. You can choose if you put the blue guys here or here, it doesn't matter. But what is important that all of the blue guys are together. So you want to have them in clusters and grouped by similarity. Okay, so in this picture, it looks quite easy to understand. Okay, we have one feature, we group them by a feature. But here is a little bit, so this is a more complex problem. I mean, it's a little bit more complex, but this is something that you can get in real world. So you have actually more features. You have, let's say, 2 features. And in real world, you can have 3, 4, 5. It doesn't, a lot of features. So here, grouping now is not so intuitive anymore. You can do, so we have shapes and we have colors. So let's say those are 2 features. So if you look at this picture here we have a grouping, or actually, okay, let's go here first. We have a grouping here by color only. So the shapes are together, doesn't matter which shape, circle or this square, but they're grouped by color. But maybe this is not what we want. And also, if we rerun the unsupervised learning, because of the random initialization, we could get groups like this. So maybe we have the circles outside and we have, let's say, the squares inside, but still they're colored by, they're grouped by color. And a third example is, okay, we actually do not group them by color at all. We just group them by shape. And it depends what you want, actually. Sometimes maybe you want to have something like this because, yeah, maybe you want to have behavior like color together, and then you want to know where is the boundary and where these squares start. But sometimes actually want to have something like this. And I will show you why in time series, sometimes we actually want to have this. We want to have all of these guys grouped together, and we should not consider the color. And this could be a feature, and I will tell you later what this feature can be. Okay, so now that we have this intuitive, I think, understanding what grouping is, so we have some data, we have some features, and we want to group them in a certain way. And if you're doing it with, let's say, models where you cannot influence how they're grouped, the grouping can be in different ways, and you cannot influence it. And also, if you rerun the algorithm, the grouping can be different. What contrastive learning is going to do for us, that we can give them some kind of information on which guys do we want to have together. And this is actually what this does. So you say, please do not look at the color, just look at the shape and put all of the similar shapes together. Okay, so here is a picture of contrastive learning. So basically, contrastive learning is this idea that you take a batch out of your data and then look at each sample individually. Then from this sample, you make some kind of augmentations. In this case, I took augmentations like changing the shape because I think it's a little bit more easier to understand. So basically, we have this, our object can be an ellipsoid or a circle, and then we can change the shape. And we have different shapes and different colors. So these are the 2 features we are looking at. And then what we can say is we take one point, or let's say one data sample, and we create new augmentations. So 2 new augmentations. So this guy and this guy come from the same data. And then what we say to the algorithm is, please group all of these guys together. Please push them closer. And please push all of the other guys further away. So for each of these samples, we create 2 new augmentations. And then we say, please, for all of these, put them together to their origin, or put these guys, okay, actually, put these guys 2 together and push all of the other augmentations away. So what you get at the end is that you can actually choose some feature, or it can be more features depending on the augmentations. You can tell the model which guys you want to have together, and of course the other ones are going to be pushed away. So please try to remember this figure right now, because on the next slide, I'm just going to show the equation for this. I mean, the equation is exactly shows exactly the same principle. It's like you want to minimize the distance, or you want to maximize the similarity between these two guys, or between all of these guys, and you want to minimize the similarity, or basically you want to make them dissimilar to all of the other guys. So here it is. Like, this is the contrastive learning equation. This equation was introduced in a simple framework for contrastive learning of visual representations. I've also put a link here to the paper. Really good. Please read through it. You have much more details. So here is the original paper. Here is the original figure from the paper. So here is one data sample we take. We make 2 augmentations, and then we say, for these 2 augmentations, of course, we have to go through some network. So here they have 2 stages, one F and one G network. And then they get some kind of representations. And then what they say, please maximize the agreement between these 2 pairs. And please, so minimize the agreement with all of the other pairs. And this can be seen here. So here we have this zi and zj. These are these guys. We want to maximize their similarity. And we have here all of the other pairs. We do not take we do not measure the similarity between yourself. So, of course, if you cannot go with zi and zi, so you push away. So here, this we want to minimize. So you want to push away all of the other representations. And then at the end, what you do is you sum all of these terms. So why is this useful? So I've been talking a little bit about clustering, but this can be applied on any kind of learning. Actually, it's also really prominent in computer vision, where you have some images and then you apply different kind of augmentations. Maybe you change the contrast and so on. And what you say is like, please, you have this image. It's an image of a dog, and you have different contrast. Please put them together. Yeah, this is shown on the next slide. There is also another interesting paper called Supervised Contrastive Learning. Here, okay, so here left is the example I showed you before. I showed it with my object, but here is with images. So you take one image of a dog, you crop it, maybe you change the contrast and flip it, but you want the embeddings to be close to each other, and all of the other ones you want to push them away. And the network then puts together all of the similar objects. What is important to notice here is that here it says normalized embeddings. So normalized basically means that we will have all of the embeddings on a unit sphere, circle, or hypersphere, depending on what the dimensionality of the latent space is. And actually, this is not really good for my approach, for what we want to do for clustering, because if we really force all the embeddings to be in a unit circle, then you really reduce, or you reduce the freedom of the network to put the embeddings wherever. Then you are constraining it. So later, I'm going to show you that in my approach, I do not use the normalized embeddings. What is also important interesting in this paper is that they also use the labels to put like dogs together. So it's not that they only put one image and their augmentations together. They also put other dogs together because they have labels. But Jörg is going to talk a little bit more about this, because I do not take any labels. So for me, I really do unsupervised learning. Okay, so now on the next slide for time series clustering. So I've talked a little bit about clustering in general. You want to put guys points that are similar together. I've talked a little bit about contrastive learning, that you can actually say which guys we want to have together. And now we come to this time series clustering. And I will then say why I think the contrastive learning is really useful for time series clustering. So generally, how you process time series clustering is that you have some kind of sliding window. Now, actually, before that, I'm just going to maybe tell something about the signal. This is hand-drawn, but I just wanted to show you an example. I mean, this could be anything. This could be any kind of signal coming from a machine, or maybe some activity tracking. I don't know. Maybe it's not even. It doesn't matter. What matters is that here we see some kind of 2 shapes. Let's say these are 2 activities which we're interested in. And normally, how you process this is that you have some kind of sliding window, and then you slide through the data, and then you try to say what is what. And especially if you do unsupervised clustering, then you just do the windows and hope that the network finds something. The problem with this time series clustering and with this sliding window is that, let's say we are interested in this signal. This is some specific activity we want to find. So here, if you consider the first window, this is the signal we get. And if you consider the second window, you see that it's shifted a little bit, because as you do sliding video, you never know where you are exactly going to cut the signal. So for us humans, it can be obvious that this is the same signal, and we could say, okay, this is, yeah, looks similar, it should go together. But for the network, actually, it could think, okay, wait a minute. This signal starts here and ends here, and then I have some 0 here. And this signal starts here, and then I have, it's not so similar for me. So what you can get, actually, what happens quite often is that one feature on which the model is grouping these guys is on where they start and where they end. And this is actually something which you do not want. I do not want to have the signal grouped by where it starts and where it ends, because this is this stupid thing that happens from this sliding window. So what I want is actually these guys to be together. And I'm going to show you with contrastive learning how we can do this. So here is another example. So here you see this activity quite prominent. You can see, okay, this is a signal. Here it starts pretty much at the middle, and here it starts at the beginning. And the network could say, okay, I'm going to group all of these guys who start at the middle on one place and these guys on the other place. Okay, so joining, so here I just wanted to tell you right now. So this is actually this problem I had from the beginning. So I want to group these guys together. So I want to find this signal. So this is, let's say, my circle. And I want to find the other signal. This is, let's say, my square. But I do not want to take, I want all of these guys to be together independent of the offset. So the offset could be like blue could be positive offset, red could be negative offset. I do not care. I want all of these guys to be together. So you can actually consider offset as another feature. And normally, if you use really unsupervised learning, you cannot influence this. But with contrastive learning, you can say, yes, please put different offset together. And this you actually do by augmentations. So you take one window. This is like the first signal, and then you say my first augmentation is I shifted a little bit to the right or left. I mean, it is random. So basically you shift it randomly for some value. You shift it again randomly for some value. And then you say, please, network, put these guys together. And then, of course, you will have in a batch many other signals. And then you say, please, these guys, put them together, and please push the other guys away. So here is so here is again the contrastive learning and the formula. What I want to just say is that I didn't use a normalized temperature scale cross entropy loss, because if we normalize it, as I said, you will have all of the embeddings in a unit circle. I do not want that. What I want is to have clusters which are freely, they can move wherever they want, and I also want to be able to inspect them visually, so I embed them directly to a 2D latent space. So for the example in the next slide, I used inverse distance as a similarity, and later in my code examples, I will show you an example with cosine similarity. So as I said, what you want to do is maximize this guy here. This is like the two augmentations, and you want to minimize all of the similarity with all of the other pairs. Okay, so this slide just shows an autoencoder, because autoencoders can also be used for clustering. And I just wanted to tell you that if you're using contrastive learning, you can omit the decoder part and you can only use the encoder part, because you directly go to the latent space where you want, and then you do the loss on this latent space. And I also show it here, an autoencoder, because I will show you some results if you use an autoencoder, and I will compare it to a contrastive, to an encoder using contrastive learning. So here are some results. I cannot show you the signals which I used, but I will show you an example, some let's say generated signals. What I want to show you here is that we had in this case some labels, and we were interested in these two classes. So one was the green class and one was the orange class. And if you use an autoencoder and t-SNE is basically a dimensionality reduction similar to PCA if you know. So t-SNE is basically t-distributed stochastic neighborhood embedding. So what he does, like the encoder, the latent space is, let's say you take 16 or 32, and then you just convert it with t-SNE to 2. So this is only for visualization purposes. So what you can see is that basically you get these groups. All of these green guys, you would like to have most of them together, but because of the offset, he groups some of them here. The offset, like the signal happens at the beginning. Here, maybe the signal is happening around the middle, and here maybe at the end. And then the network does not know that these guys should go together, so he puts them wherever he wants. But here on the right side, if you consider encoder with a contrastive learning, here we told the network exactly, please ignore the offset, put all of the signals which are similar independently of the offset together. You get this, so which is much better. So here we get really groups which are really close together. These could be some outliers or some misclassifications or some signals which are really similar to some other signals, but basically the majority of the signals are grouped together. And here also what is interesting to see is that we have really a great imbalance in the data. So these are really, these two clusters are distinct, but they're really small compared to the other clusters. So basically, if you remember anything from this slide, from my talk, this would be it. So if you use, let's say, autoencoder, and you will get something like this. You will get some clusters which have together signals, and maybe even the signals you want to find. But the problem is that if you're considering offset, he can put the ones with a different offset to a different location. And with contrastive learning, you can have them together. Okay, so basically this concludes my talk. Here I have also a slide for the the presentation part. I still have the code part. So here are the references of the two papers, and later when you have the PDF, you can find them. Okay, I'm just going to switch now my streaming to Firefox, and then I will continue with the code part. So just give me a second, bear with me. So here. Okay, so it's streaming. Okay. I hope, I think you can see it, right? Let me check in the Twitch. Yeah, okay, you can. Perfect. So here is an example of contrastive learning applied on time series data with some, let's say, dummy data or some generated data. But I think it's still, you can apply this directly if you want on your example and just change the data. Yeah, so it's, even though it's dummy data, I think it can be directly applied. So for the similarity, as I said, we're using cosine similarity. The augmentations, I use only, let's say, one, but also I use a noise. Just, in the dummy example, I also put some noise, so I also use in augmentation some noise. So this will depend on the data. If your data does not have so much noise, you can omit this. But basically, the shift I would always keep, because if you process it like with a sliding window, then it's this is something which you want to have. So the augmentations are just basically shifted randomly left or right. Here we say -5 and 5, and then also add a little bit of noise. This is now the implementation of the contrastive learning loss. First, what I do is I get the 2n data. So what I do is, like, when you give me a batch of data, I will create 2n, basically 2 augmentations. So for each data, so like each point in the data, please create 2 augmentations and append them. And then later we will say, please put these guys together and the other ones further away. So let me run this. So here is basically where the loss is calculated. So you pass you pass for the 2 batches, for the 2 augmentations, you pass for all of the augmentations on the batch. You pass the encoder values. So basically the zI and zj's. And then what you do, I mean, I will not go too deep into this, but basically you create a cosine similarity between all of them. And then what you do is you create the loss at the end. So basically you have here the denominator, which are all of the positive pairs, and you have in the denominator all of the negative pairs plus the positive pair. This is a little bit better explained in the paper, but the idea is that this will always be normalized, and it cannot exceed 1. So basically, because this guy and this guy, so if this guy is 0, it's going to be 1. If this guy is bigger, then it's going to be less than 1. And yeah, basically at the end, you sum all of them together and you get the loss back. So yeah, basically this is just a vector implementation of the equation I showed you before. So let's run that. Okay, so here we create our data, and I'm going to show you how the data actually looks like. So we created 10,000 samples, or 10,000 time series. And then the time series length is 50. So here, if I show you the signal, so basically here is like a Gaussian function, positive and negative, and then we have another one with higher width, let's say, or standard deviation, and then we have here, let's say, plus and minus. So we have one Gaussian function and another one at the middle. Just make a minus. I mean, the signals are really not so important. You can play around with the signals, but basically the idea is that these guys can be shifted, and also that the augmentation shifted. This is important. So here, basically, when I create the data, I always create randomly some offset, and then this. Okay, so let me check why. Okay, let me do it. Okay, is it on now? Let me see. Yeah, okay, should be okay. Perfect, okay. Okay, so 10,000 examples and time series 50, 50 samples. And yeah, so currently I tested with different kind of distributions. So you can choose here at the beginning, if you want to play around, you can choose which ones you take with which probability. So I wanted to show you that even if your data is not distributed equally, you can still use it. So here you will see like 40% of the data is basically the last class. So this guy, I mean, we can also change it. It's not important. So you can play around and change the distribution. So it's not uniformly distributed. So there are more of these guys than all the rest. Okay, so here is the model I use. So I use a convolutional model. So this is basically just a convolutional network. And at the end, you get a 2D representation. So basically, you get the two numbers. It's like for every time series you put in, you get two numbers out. And this is like the 2D latent space I used. So let me run this code with this block. Okay, so nothing special to say about this. It's just like a convolutional neural network with several layers. And at the end, you have two linear layers. The non-linearity is ReLU, and at the end, it's linear. So basically, yeah, the guys who are familiar, or girls, or I don't know, everybody who knows about neural networks knows can recognize this. Okay, so now I create the model, I create an optimizer, I say from how many epochs should it run, and then also I define a batch size. And here I just have a small training loop, nothing fancy. I just have here, I plot the results after every 10 epochs. And then here I have the forward pass and backward pass, and here I just create the augmentations and run them through the model. And then later I create the loss with this output. Yeah, so basically you give it a batch, you get out the augmentations, run the augmentations through the model, and then calculate the loss with the results of the output of the model. And if you run this, so this, like the beginning, this is what you get randomly. So you see like the data is jumbled and these guys are all over the place. The group here is like nowhere to be seen. And then after, let's say 10 epochs, you already see, okay, the network is starting to pull apart and push apart these guys. So what it does, it gets like a signal from here, and he creates two augmentations, which are probably similar to some other signals from here, and then he puts all of them together here and pushes all of the other ones away. So yeah, and I will let it run for a little bit, so just that you see what's going to happen. And also because you're using the cosine similarity right now, what you're going to see is we will have these clusters which are a little bit elongated, because if you consider the cosine similarity, all of these are similar. They are really close to each other because they have the same, let's say, angle. So if you look at in a vector, if you consider that all of these are vectors, they're pointing to the same direction, so their similarity is quite small. That is why also I considered other similarity scores like inverse distance and so on to avoid like these elongated clusters. Okay, so here, it starts to push them, pull them apart. As I said, this will also depend, like the results you'll get are going to depend on the random initialization at the beginning. So I didn't fix the seed here on purpose because I'm going to do a second run so that we are going to see we will get slightly different results. But what is important is that these guys get grouped together. So let's go further. Okay, so it's almost there. So we have almost all of the classes separated. So this guy is really separated. He was separate from the beginning, I think, and these guys are going to be separated later. Of course, you have to let it run for some time. Okay, so I was just going to do quickly another run, just that you see that it really is random and that you will get different clusters. So here we had the purple one on the right side. So let's interrupt him. Okay, and yeah, so let's create a new network and let's run it again. Okay, so different installation. Maybe even it's going to be easier for the network to separate it right now. So maybe we will see better results. So immediately we see it's different. Okay, this guy is pulling now on the top left corner. But yeah, basically this is it. This is what I wanted to show you. So we have some signals, we can augment them, and we can basically create different offsets and tell the network, please put the offset together. And what the network is doing is grouping them then together by our augmentations. So because he's grouping them on the augmentations are really important. If you do not create your augmentations properly, so if you do not, you have to have at least a little bit knowledge about your data, because if you create some crap augmentations, the clustering is not going to work. So let's say if you only created, let's say, randomness as your augmentations, you wouldn't probably get like one big cluster with all of these offsets. So yeah, there is a standard, let's say, augmentations you can apply on time series. That's like adding randomness, shifting the signal, stretching it, shrinking it, and so on. So you will have to play around with them a little bit. But yeah, okay, it seems that this time it was easier for the network to separate the classes. So almost all of them are separated. Yeah, so yeah, basically this is it. This is what I wanted to show you. So all of this, like my presentation, actually, and your presentation also, and all of the code is going to be available. It's available on GitHub already. We are going to send the link, and you can have a look, play around with it. And later we're also going to have a Q&A. I think I have some time for some questions. Yeah, okay, maybe not. But yeah, later we have a Q&A, and then we can have a discussion. You can ask what you want. Okay. So yeah, that's it from my side.
Okay, thanks. So I will continue. So thanks for the cool introduction to this clustering, Halil. And I think you really already get an idea what this whole thing is about. And I will also start with a presentation. Let me quickly share the screen. Okay. And start it. Okay, yeah, so welcome to the second part of this talk. You already heard something about clustering from Halil, and I will first give you some info about me, like Halil did. I'm in my PhD program. I am actually using deep learning to detect human factors from biosignals, supervised by Professor Eduardo Weers and Herbert Danzinger. I sometimes have very sparse data or fractioned data sets, and this is a problem with deep learning. And the talks I did before about interpretability, but also the contrastive loss, have a lot to do with this problem in this domain. So generally, I think a lot of this idea with deep learning is that there are now a lot of deep learning troubles. Like you have no or few labels, you have fragmented data sets, you have noise effects, you have time shifts who have an effect. You want to do clustering. So the time shifts who have an effect in clustering, you just heard from Halil. And we want to solve that. And contrastive loss is partly a solution for some of these problems. So we've already seen clustering and time shift. And we will see with few labels, with fragmented data sets, and with noise, how to deal with that in my talk. But first, let me give you a little bit of the history of contrastive loss, because it will, I think, give you an idea about some of the things it solves. So contrastive loss was first introduced in 2005 for face verification. The guys who introduced it were Sumit Chopra, I don't know if I pronounced them right, the name, Hatzel, and Jan LeCun. You for sure know Jan LeCun. What it was actually back then used for is they used a data set where they had people, and they had people who look similar to them or different ones, and they wanted to actually make a metric. So they first introduced the first version of the contrastive loss term, which was a little bit different back then, but it was the same idea as we heard all the times now, is that there was a positive and a negative pair, and the loss term is there to push the positive pair nearer together and the negative pair far away in the domain of images. However, back then, I think the term which sticked most in the head was the term of Siamese networks. So what they did is to use the convolutional neural network to run the images through, use the specific layer towards the end, and then made pretty much a Euclidean distance as the basis for the loss function. And I think this idea to use the same network for two different samples or for several samples will stick with us all the time. You also saw it in Halil. He used actually the same model. So the next milestone was 2012. Back then it was still called NIPS, now NeurIPS, where it was on distances on images. The guys who worked on this, I think you most likely know Ruslan, I never can pronounce, Salakudinov, the name. And they introduced, actually they called the loss different. They call it triplet loss. It's still a form of contrastive loss, but it doesn't have like just a positive and a negative pair. It has an anchor with a positive and a negative version. And they actually used it more or less for retrieval, because you learn a distance, and they showed that, for instance, if you use a Euclidean distance, really like on the pixel wise, you get a lot of wrong results. But with this triplet loss or the contrastive loss, you can actually quite well get the things you really want. So we see in this presentation, they used different sizes on the embeddings. And this is the next term we'll stick with. Besides Siamese networks, we usually say in contrastive learning that you run it through the Siamese network to get an embedding of your representation. You want to have these embeddings in this feature space near to each other when they're similar or far away. They actually called it metric learning. Also, the paper is called Hamming Distance Metric Learning, and they introduced now this term, and this is also in the community used quite widely. So we get a confusion. Some people talk about Siamese networks, some about triplet loss, some about metric learning. It's all in the framework of contrastive loss. Some other important milestones. I think 2018, we had the first application to sensor data. We had speech emotion recognition with Siamese networks. And I think really this year where contrastive loss got really popular, first by the paper which Halil also already mentioned, where this newest contrastive loss term, the xent contrastive loss, used as, that's why in the title we said contrastive losses. There are actually several terms, but now this xent is, I think, the one many now kind of refer to or use. And there's another paper, and this got this whole idea of using data augmentation on one and the same sample to kind of mitigate effects from the data augmentation. Like you really, as Halil said, you have to know something about your data, and like contrast away these effects to other effects, and without working without any label. The second, the big self-supervised models or strong semi-supervised learner, was already where they really then looked on using just 5% of ImageNet data. They actually went to state-of-the-art results for image classification, which is obviously an immense reduction. And maybe also interesting for the reinforcement people among us, from Peter Abil 2020 was a paper, curl, contrastive unsupervised representations for reinforcement learning, where they basically showed that you can use that as a multitask learning target. Actually, the people for speech emotion recognition also used it as a multitask. So you can actually use two losses, the contrastive loss, and in speech emotion recognition, it was just cross entropy. And here they also have the reinforcement learning loss and contrastive unsupervised learning. And they could show that they can, also for reinforcement learning, have a way better sample efficiency. Okay, so far for the history of everything. So let's go a bit into my work. So what I'm currently working on, just give an example, is like, for instance, you work on human factors in automotive with biosignal. And just imagine you would, for instance, have a driver of a car, and he is kind of, you sense his physiological signals with some modes, like if he's alert, normal, drowsy, or asleep. And now, just for the sake of argument, it's not exactly that way. Let's say you gather data from your own experiment and from 3 other sources. And they're all what a research group could do, or also what a company could do with some resources. So they are all not tiny, but also not large enough for deep learning alone. And they all use slightly different sensors. The same type of sensors, but slightly different. What I mean, for instance, we have on this picture 2 galvanic skin response sensors, and they have a very different noise, for instance. So the idea with contrastive loss is I want to, since I know how sensors differ, model that into my augmentation and transform these embeddings into a space where these differences are mitigated, but you could still learn something about the signal, and then you fine-tune a classifier on that. So this is the whole idea where I use it. Bad news is these datasets are all confidential. You have to sign something until you publish. You cannot show anything. So I made a surrogate task. Let's talk about that. So instead of the thing I'm really working on, I kind of made a small example for this online talk, where we are about, which I said, unifying sensor recordings for later supervised training. Let's imagine we have some fantasy device generating a signal. And this signal, as you can see, is consisting of sine waves, of some kind of random peaks, some spikes, some squares. And they're like not evenly long and kind of randomly appearing. If you are already in the GitHub, you can actually generate your own signals or play around with it. If you go to the problem description, IPython notebook. I hope I already uploaded that. Thanks, Herbert, for the link. Yeah. So we have this signal. Let's imagine now we have 2 different sensors reading it. And we can see sensor 1 in this picture has a higher sampling rate, I think, a lower sampling rate, but more noise and some offset, some drift. And sensor 2 has a higher noise, but a higher sampling rate and no drift. But they would be still the same signal, and we want to use the power of contrastive learning to bring them into the same space. To be more concrete, to be more on my use set, it's like we have 4 data sets. They all have a little bit of different signal and 1 sensor per data set. So that actually means you cannot calibrate one sensor against another by just comparing the noise of the same signal, because it's never exactly the same signal. You can just, you need to do something else. Yeah, this is what I just said. So this means we can actually, first of all, bring everything into a common representation for time series. You also always want to have them in the same thing, like for instance, 100 Hertz representation. And we assume that the augmentations we need are noise, because this is a typical problem of a sensor, are changes in sampling rate, so downsampling, upsampling, and ablations, so small parts of sensor failure. Let me quickly see if I can get this pointer working again. Remote. Looks, I think, good. So up here we have the ablations. So here, for instance, augmentation ablates a small part of it. Here we have changes in the sampling rate. It's the same signal, but some points are removed. And here we, for instance, add noise to the signal. So I guess it's a little bit more a sinus in this side than on this, where some peaks are a bit stronger. There is a own utils file online where I just added these simple augmentations. Again, I then do pretty much the same as Halil as a basis. So I draw one part of the time series, a random segment out. I don't know what it is. I run it through these Fs, and this Fs is now, since we know in the history, this is the Siamese network. G is another nonlinear projection. The reason why this is in the paper is that you just don't want to force your network too much to be near further, because you actually, with the augmentation, you do change the signal, so it's not the same. And you usually throw away this projection head. Okay, so Herbert already showed the link to the GitHub, and so I will now, let's do it with the browser. We're here. Okay. So I think if you go there should be some notebooks. I think I already mentioned problem description, which kind of shows again how these signals are generated. Or you could also look at data IO, where you see a little bit more on what can be done with data augmentation. I don't go into detail on that. I think the most important thing are the contrastive loss example, where I actually do almost the same as Halil. So I will skip over it a bit. So in the first part, I prepared the data set in more or less on a similar way as I showed in the presentation. So I simulate now 4 sensors. They all have first generate their own signal, and then they actually capture the signal with 40 hertz or 80 hertz and with noise of 0.3 and so on. So 0.3 is a lot because we have values in the range of plus minus 1. Then what we want to do is we want to have either ablation or add noise or a random downsample, and with transforms random choice is another way. So it's funny because like Halil and me almost have the same code, but we did it a little bit different. So it's good to. Okay. Danke. So is this better? I will also go on Twitch again. Okay, cool. Okay, so let's then maybe here. So what I said before is like there is problem description and data IO where you can just see how this works, this whole augmentations. As a framework, there is utils where in NumPy you have all these generating of, like, for instance, the time series and how a sensor is created and so on. So you can just read into that if you like it. There is a torch utils where you bridge this thing to create a data set which you can shuffle, iterate, and put transforms on, and how to really do the transforms with this NumPy code. In case you're interested, you can look there. And then the really interesting thing is first the contrastive loss example, because this is where I do the pre-training to mitigate the sensor effects. And as I said, this loss is very similar to Halil's. This code is very similar to Halil's code. And what I basically do is, let's restart that kernel still, is here I actually simulate similar set. with as dataset, which is described in the slides, with 4 sensors, which would have, like, for instance, 40 hertz of sampling or 80 hertz of sampling and some noise, and they all have their own signal. When I do that, I also need transforms for later. And then with that, I can generate the data set, which I won't do now. I will just load it from a pickle because it's a few hundred MB and it takes a while. And then the rest here goes quite classical PyTorch. You want to have like a valid, test, and train data set, and you can still just do that and see if there's a GPU or not. So this is on my laptop, but it actually, which has no, it has no NVIDIA GPU, unfortunately. But you will see for this example, it's fine enough. So on the train loop, I think the important thing is if you iterate through the data set, I return. So the way I did it is not have the function of how little, but I used, this is maybe interesting, in Torch utils, when you do a data set, you can actually, maybe you see it better here. If you do a data set, then you can, on the get item, just say for one item, I want to return 2 things. So on apply transforms, if I want to return 2 transforms, I transform the sample in 1 and 2, and then return the tuple and the label. And then, let's go back here. Then obviously this is returned as a combination. And yeah, then it's here I just correct dimensions. But then it's really similar. So again, the Siamese network is some network I define, and I run one augmented through the model and through the same model the other augmentation to get the embedding, and then I run both embeddings through the projection, and then I calculate the loss and just go backward and do the same for a validation step. And so I tried it with inception time, because this is like one of the state-of-the-art CNNs. It's like InceptionNet or a simple encoder, which is very similar to the encoder of Halil. And you can just load them, do some hyperparameter tunings, and let that train. It's that the results are pretty same to Halil, so let's just not go into detail on that. And then what you want to do then with that is you want to then use this thing to fine tune. Let me quickly see. I think there's something still open here. Let's restart it. So so what you do is you actually load again your model you need, like the ones you did use on the unsupervised pre-training. So for instance, I have some model I trained before. And you also load your projection. You don't need to usually draw it away. You could just use a different projection head and randomly initialize it. And in the last paper of Hinton, they actually said you should use the first layer of the projection. And I think this is or actually I have to now admit that I played with that around while Halil was talking and messed it up a bit. So let's just explain the rest of the code, and then I will go back to the presentation, see if I can fix it. Maybe in Q&A can show you the real result also. But let's. Here I said we want to simulate the case that we have little labels. So the whole idea of this thing is like, imagine you have like a lot of experiments where a sensor and some physiological data is used, but only some are in your domain. So maybe you gather all this data set and unsupervised train with the contrastive loss. And then you, with the labels you have, you fine tune on that. I did that in that case that I changed the splits. So my test size is now 60%, a valid of 20%, and I only train on 20%. Rest is exactly the same. Also check the GPU. And now the train loop again is almost the same, just that we have the time series and labels. And you see that I changed here code. This I didn't get an error because I'm working on a CPU. And now I run the time series just once to remodel. I don't have a second augmented version. This actually with the train data set I give, it always gives me an augmentation. And I use this now as an embedding. And actually, as you see up here, my model is actually changed to not being trainable, because the whole idea is that I have like this one deep neural network which gives me the data into a space where I have embeddings where they are actually near of each other, and then I want to train something on top on that. So this is important. So I still now use the projection for something else, namely for fine-tuning. So I have the same criterion, and I do very classical PyTorch backward and the step and update the validation. And then I can use cross entropy and train. And here I said I have an error on that, which I just messed up. I don't know. So this is the idea. What you get is in this case it's actually not it's a simulated data set and a very small contrived example. So also the accuracy isn't too good, but it shows you the whole pipeline. Yeah. For my examples, I think it really shows a good promise with the physiological data, but there I'm not finished in experimenting with it anyway. So I can't tell you results on that, but it looks promising so far. That's what I can say. So let's go back to the presentation and do some summary. So Halil showed you how to use contrastive loss for clustering. He showed that you kind of get data out and you want to, for instance, cluster the colors, but you also have shapes. And you also, in his case, want to mitigate the effects of the shapes. So you do augmentation to change the shape randomly of the same example where color is in. And with that, actually achieve clusters which mitigated one effect but kept the other one. In his concrete example, he was looking at shifts of windows in time series data so that this effect is mitigated on the cluster. We also looked a little bit on the history of contrastive learning. We saw that it started with in the image domain with face verification. It then went to actually still in the image domain to be a way to actually query for images based on an example image. And also in 2018, we actually saw the start of it being used in sensor data. And in 2020, again, in the image domain, we showed that we can use it to greatly reduce the amount of labels we need, or to use it in reinforcement learning. And I quickly showed you the idea how to actually do this also with a specific setup when you have fraction data set and not a lot of labels. How the pipeline would be to train on that. And I'm also keen to show you more exact results with my real work as soon as they're finished. So that's what I'm currently spending most of my time on. thanks for the attention, and we will continue with a Q&A in Discord, and we will post.
Okay, thank you, Jörg, very much for
You're
your
welcome.
presentation. And yeah, I'm glad some people said thank you. I'm glad. I hope you learned something. I also want to say sorry for the mic not working at the beginning. I was told that I was really frustrated. I was. What can I do? It was really frustrating.
Yeah, we all had our problems. I did the classical error you shouldn't do, changing something at the end.
Don't change.
Yeah, which I know I shouldn't, but yeah. Anyway, let's deal with that in a bit, and you get an update. But yeah, in the end, I think you saw the pipeline and the important things. But maybe we now just switch to Discord. So there is a link. I think Herbert already did. So Herbert actually posted it a while ago, but maybe let's post it again. I should have it here. And so we can question and answers. Oh yeah, perfect. Here it is. Yeah. So let's go out here and let's meet in Discord. And I hope you all have interesting questions. Okay. Bye.
Sessions.